computer remote, right? Yeah, so it comes from the data set that it was used to train the particular version of the machine learning model. And then if we think about it, it's what makes these models useful. Because if I'm, I don't know, training a camera that goes on a car, it wouldn't be very useful to train a model to find birds, I don't know, different kinds of birds. But I would like that model to perform really well on the things that's going to be seeing with other cars, motorcycles, bugs, on the street. So that's how we are going to change the behavior of models without changing structure. Okay? I answered. So coming back to the metrics, we're going to do the mean average precision, which provides a single number that summarizes the overall performance of our object detection model across all different classes and different intersection over union thresholds. Okay? So this probability that I was thinking about comes from the thresholds of intersection over union that exists between multiple predictions. Okay? And then precision is how good my model actually finding the object that it's for. Recall is how many mistakes it makes by detecting things that were not what I was for. And accuracy is basically how good the true positive and true negative, that means the things that my model did well against everything that my model did, right? And so we're going to call that accuracy. Those are the metrics. And the mean average precision is going to be the area under that curve over there. Again, it's going to be a number between 0 and 1, where 0 is my model does not perform. And 1 is my model is perfect and makes no mistakes, finds everything that it needs to find, and doesn't mean, right? And we do that at a certain threshold. So that's why when we see tables of precision, it's usually map at 0.5, right? And so that's a single curve. And usually, we're going to do a series of those evaluations to decide how we're going to our particular application and given our particular requirements. It's not the same to find tumors, find potholes, right? Very different risks. After, yes. So with the box, we filter, which if we don't filter all the outputs of the prediction head, we have a lot of noise, right? So we filter using a threshold. And at that particular threshold, we take a measurement of precision and those we decide how does it look. And one axis we have recall on precision, and so we know how good is my model finding everything that I find without rejecting any student. After we have trained our machine, we usually want to transform it something that will perform more efficient inference. Basically, there are two important moments in the life cycle of. One is training it, that means teaching it, which is a very different task than we're actually using it. Train it, want to feed as much data as possible, as fast as possible, so that we know how so that the model learns how to behave given the nature of the data that we're feeding. Or doing inference one by one, any examples at a time. But usually what we want there, the fastest response every time we call the model. For two very different trains, and that means our model needs to exist in two slightly different optimized for each kind. Good. With OpenVINO, is Intel's toolkit for inference on multiple hardware devices. We're going to be doing something that's called post-training optimization, or post-training quantization, and then we're going to be using a framework called neural network compression framework. That's a very advanced tool that applies several algorithms to make our models run very fast. So we don't need to understand the fine details of this. Of course, it's very interesting, and I recommend you that if you end up deploying one of these models into production, just take a deep dive into the documentation. You're going to have fun learning about it. You're going to have fun learning about the different algorithms that you can use, a lot about the thing that you use. So we're going to be using that, and I'm going to show you the difference in. So after that, how are we going to know if my model, if by optimizing my model, I lost some of the performance in terms of metrics, the MAP that I was talking about? Well, we're going to be using a tool, benchmark tool, that allows us to feed a data set and compare deterministically how well, how worse, or how better our model. Today, we are launching, well, Intel and Hackster.io are launching a challenge. If you want to join, take out your phone and take a picture of that, because the first challenge you'll be able to join today by following the instructions. There are basically two versions of the challenge. The first one, you get some swag from Intel just by taking a screenshot of what we're going to be doing. Okay? Don't tell them that. Or tell them, better if you follow along during my workshop and got a, I don't know, from them. And if you apply to the advanced challenge, you can get a NUC. Okay, so what is a NUC? A NUC is a computer by Intel that includes new generation of processors and a GPU. And those include the kind of hardware that OpenVINO is optimized to run on. It's consumer hardware, but it's good enough for you to do some machine learning training. So, parenthesis, we have two NUCs provided by Intel for you, the community, to come and use. As long as you're working on something really learning, you're welcome to come and use two computers that are set up to my left. You can ask us about it later, and you can ask Victor about the Stable Diffusion demo that is currently running over there. That's running locally, and it's generating a new image from a different prompt. So after, if you get tired of my voice, or ask Victor with a black hat, a brief explanation about. But in summary, you want to come, if you want to play around with machine learning, and your laptop is not enough, you don't want to really be working, or paying for a GPU cloud, just come here and, I don't know, maybe be a visit for a day at Hacker Dojo, or better yet, join us, remember, okay? So that's that. And now we're going to be using this particular notebook. I'm going to be running this notebook in one of those machines so that you will be the actual performance on consumer hardware. But if you want to follow along, and I do encourage you to do so, you can follow along on Google Colab. So take a screenshot of, take out your camera and navigate to that link, or just go to github.com, OpenVINO Toolkit, OpenVINO Notebooks. So, on that repository, the OpenVINO team and the community contributes a lot of examples for you to come and learn. Today we're going to be talking about this one, the first one, right? And if you click on this Open in Colab, immediately you're taken to your Colab account. If you don't have one, just create one, and you will be able to follow along on a free instance. You don't need to pay anything to run this notebook because it can run on CPU. For this particular task, it's going to be enough. But this is not only the example that's in this repository. Actually, if you navigate to a notebooks folder, you're going to see many different examples. A lot of them are super interesting, state-of-the-art models, from computer vision to large language models, text generation, whatever you can think and dream of, it's going to be here. And if not, I invite you to find the model, contribute it, and create a notebook for the rest of the community to learn from. So this is one of my favorite repositories on the internet. I really invite you to come learn about OpenVINO, but more importantly, learn about machine learning and all the cool things that you can do with those techniques. So with that, I think this was the last slide. Yes, it was. We're going to go to the example, but before I invite you to join our Discord to discuss with the rest of the community about machine learning topics. This will take you to the Hacker Dojo Discord. I'm in there to answer your questions, and I'll be posting there a few challenges in the following weeks as well for you to win very cool prizes. So, are you ready to follow along with the example? Was everyone able to open the notebook on Google Colab? Okay, I'm gonna show it one more time. Okay. Go there. Let me know if all of you are already there. Okay, just go there and click that little button that says Open in Colab so that you can follow along. So, what we're gonna do today is we're gonna convert and optimize a pre-trained YOLO V8 model with OpenVINO. We're actually gonna run it in 3 different versions of it. We're gonna run it how it is when we download it. We're gonna convert that to OpenVINO without making any kind of optimization, just translating it to OpenVINO, and we're gonna see very interesting gains there. And then we're gonna run it through the NNCF neural network compression framework that I was talking about before, and we're gonna see amazing performance happening there. So this is our agenda for the example. We're gonna prepare the PyTorch model. If you're not familiar with PyTorch, PyTorch is, I think, the most popular machine learning frameworks maintained by Meta, open source, and very loved by the scientific community. There are basically 2 main frameworks, PyTorch and TensorFlow. I tend to be on the TensorFlow camp, but most of the people that I know prefer PyTorch. So today's example is actually comes from a PyTorch model. We're gonna download and prepare a data set. We're gonna validate the original model. That's the first version that I was talking about. We're gonna convert the PyTorch model to OpenVINO inference representation. That means we're going to make it suitable so it can run on different versions of Intel hardware, GPU, CPU, FPGAs, or whatever you have available. And we're going to validate that converted model. And finally, we're going to prepare and run an optimization pipeline to run this particular model. Now, about about YOLO V8, as I was telling you, it's created by a company called Ultralytics. And so I invite you to learn a little bit about them and what you can do with their models. There's another version of YOLO that's also published by them. I think it's V6, YOLO V6. So we're going to define some utility functions here. I'm not going to stop. And we're going to instantiate the model. This is, I'm going to make it a little bit smaller so that you can see. This is two versions of the model. I mean, two tasks happening in the same model. We're seeing an object detection model, but we're also seeing an instance segmentation output. An instance segmentation is basically a mask, pixel by pixel, that tells us, here's the dog, here's the car, here's the bicycle, right? And so we have these two versions. Why would we be interested in both things? Well, it depends. If I want to isolate the object, I want segmentation. If I just want to find it and then operate over that region, for example, to do face recognition, then I only need detection. And I might be more interested in making that happen quicker than more accurately on a pixel level, right? So those are two different machine learning tasks. The main application and how YOLO came to life was using the object detection task. The image instance segmentation task is basically the same backend with a different prediction head. That means it predicts a mask instead of a list of boxes, right? So this is the output of YOLO V8. As you could see, I ran it for the first time, and it performs an inference on 35 milliseconds, 33 milliseconds, 27 milliseconds, so around 30 milliseconds, right? Once the model is loaded into the framework. Now we're going to verify that model for inference and test that on a single image. Here, on your case, you will see that it says CPU here. I'm taking advantage of the fact that I have a GPU available on that particular thing. If you're running on a Google Colab instance, you might not be you might not be able to use GPU. You might be. You might not want to pay for a GPU, but this model can run on CPU nonetheless. So this is the model actually after conversion from OpenVINO. This is the process where we take the OpenVINO framework and just output it in a different format. And we define a utility function here. And when we run it, we can see that the output is the same output. So basically, we didn't miss any precision there. But now our model is portable. We can take this model in OpenVINO format and run it on any CPU, any GPU that we might choose. So that's the detection version. And this would be the segmentation version. Okay? So we're going to download a data set. We're going to run a validation over yes. Yes. That's why you cannot just convert all the models with the same rule. By the say, it's not like doing a multiplication and that's it. You need to actually calibrate with some examples from your data set. And so that's what OpenVINO helps us with. Now, on the first step, we only translated from the PyTorch version to an optimized version for inference, and that's just converting to OpenVINO. We're not changing the data types, we're not quantizing, we're not compressing. We're just changing the format, and just by doing that and leveraging OpenVINO, it will run faster for inference than the original PyTorch model. Now, the next step is to actually quantize the model. So quantization would be the process of converting from floating point weights into integers or smaller floating points. Okay? So that would be the process of quantizing. And then we might lose accuracy. So the earlier versions of quantization actually hit your performance, your precision very, very hard. So you really needed to make a decision. Do I want to trade accuracy in my model for speed? With these new tools, we're going to see in the end, the hit that you get into the metrics of your model is very, very small. So you won't lose. I would say it's almost imperceptible when in context with different data sets of different natures. So what we're doing now is we are feeding the COCO dataset to take some measurements of. So this will be our baseline of how our model behaves, just out of the box, just converted to OpenVINO. Because then we're going to optimize it, and we're going to compare again against these particular metrics. It takes about a couple of minutes for each version of the model. So we can actually take that time to answer your questions, if you have any. No? To talk about the data set that this was trained on. So, yes. Yes. So it's two versions of the same model. And when I say two versions of the same model, it means most of the model is the same, and only the last layers change. When we convert it to OpenVINO, so on the initial, I'm sorry, on the initial test, on this test, so here is the detection using the PyTorch model, and this is the segmentation. So we literally have two models loaded into memory, right? When we convert them, again, we have two versions of that model, right? The detection version and the segmentation version. Was that what you were asking? Yes. Yes, and then, so we have the first result, and we can see that our mean average precision at a threshold of 0.5 is 0.521. So this is an interesting number. It's not a great performing object detector, but it's very, very fast. So yes. No, you can use it with TensorFlow, and even if you have like a model that has been exported for inference with Onyx, for example, you can convert from Onyx to OpenVINO. There are some extensions for TensorFlow, for PyTorch, it's huge. I invite you to go to OpenVINO documentation and just look around. This is all the different kinds of hardware that an OpenVINO model can run on, including CPUs, small CPUs like ARMs. So if you want to run this model on a Raspberry Pi, you can. GPUs, integrated GPUs, new generation ARC GPUs, what we have here, FPGAs, even the small, what's called Movidius, neural stick They don't make it anymore, but it was a small accelerator by Intel. You can check that out as well. And it's a different framework. So you use PyTorch and TensorFlow to design and train your models, right? So you decide. So I'm gonna have like, I don't know, 60 layers, and they're gonna have this shape, and they're gonna be interconnected this way. So you do that in PyTorch, and then you train it in PyTorch, usually using a GPU. And then when you have your model perfectly trained and you have your weights, and you want to use that for inference, usually you will be converting that model into a different version for inference that will perform better, will use less memory, and will allow you to make a better use of your hardware for inference, right? So the most common approach for that is a framework called ONNX, ONNX, which is like a standard way of encoding the model for inference. OPENVINO is a version of your model that you can take and deploy without converting again to a GPU, to a CPU, to an integrated GPU, to a small GPU. You take the same exact files, deploy it everywhere. And so that, when you're talking about an operation where you're updating your models frequently or have many different machine learning models in the wild. Yes. Right. That would be like the next step is, after you have it in OpenVINO, you substitute the process called quantization. You quantize the weights from floating point to maybe a smaller floating point, integer, 8-bit, 4-bit. There are many different algorithms. And then you can even go a little bit further than quantization with the compression framework, where it's basically kind of like a tree shaking of the model, where you get rid of the paths and stuff that you don't really need on inference because it doesn't happen very much. So it literally makes your model smaller. And so that's like the... Yes, it's a smaller file that you can put everywhere. Yeah. Yeah, I use it for inference, and I learned about it when I was running a hardware company. So I was working with embedded systems, very small systems, and I needed a way to run machine learning models on those devices. That was like 4 years ago. Yes. So what's the question? I'm sorry. When you convert from the framework that you use to OpenVINO, usually you don't lose any accuracy or whatever, because the only things that's going to change is how the operations are implemented. You're not actually changing the values of the model. You're keeping the data types. But once you quantize, then you're going to get a hit, right? So how does quantization work? Well, if you think about it, a floating point can represent a huge universe of numbers in a finite length of bits, right? But the data that you're actually feeding doesn't use all the range in your floating point number. It only uses a very small region. So that means you can do two things. You can better distribute all the values available on those bits, and you can have a better representation of the numbers. For example, an integer, which is continuous and monotonic, instead of a floating point that has more like a Gaussian distribution of the models that you can represent. Right? Yes? Yes, so OpenVINO allows you to make your model first portable and lightweight, and then optimized for inference. And how is it optimized? It's optimized to the data set that you're feeding it when you convert it. So it's not the same to have an object detection that anyone can use and anyone can deploy on their systems and just use. Then if you take that, like that object detection and fine tune it to find tumors in mammographies, right? And so you make it perform really, really well. It cannot find people anymore. It can only find tumors from medical images, right? That's a very different distribution of how the numbers will look as matrices in the images versus full color photographs taken by tourists in the wild, right? So when you convert it, you actually feed it a part of your data set to make sure that whatever losses you're getting are actually away from your distribution, and that your model will perform better on the distribution of the data that's closer to the data set that you're feeding. It so that's a trick question. um, if we think of a machine learning model, we need to think about it as two things. Every machine learning model is two things. It's an architecture, which is how structurally are mathematical operations executed in a sequence when we feed data through it. And then there are the weights, right? Which is what we actually learn when we train a model. And those are literally the weights of a weighted sum that happens in one way or another across our model. If some of our weights are like out of bounds completely, it can be for several reasons. One reason can be that particular layer is not really doing any job, and that neuron is really doesn't matter. It can be a bug in my data. It can be a bug in my training. It can be a bug in the framework. But usually, if you have like those out of bounds operations, it means that it doesn't really matter if when I have evaluated my model, the results that I got were within the bounds that I expected them, right? So if you think about that and then think of OpenVINO quantization process as the process of taking part of your data and making sure that the parts that matter perform well and the parts that take a hit are actually the ones that don't really matter for your use case, then yeah, those out of bounds weights. Um, I don't know if it can make that kind of exceptions. That's an interesting question. Like, can it make like special treatment for yeah, I suppose if it decides that it needs to be like that. Although I don't know, again, if it can selectively decide to not convert all of the model. Yeah, so, and that's what we actually care about, right? We want our model to perform well within our bounds. So, we can see the validation of our segmentation model. So this is the performance. If you look at the segmentation output, you can see that there's the two outputs, right? There's the segmentation and also the detection. So on the top part, we have the metrics for the detection part, and on the bottom part, we have the output from the segmentation part of the output. So these are reference numbers that will be interesting for us to know once we do the next part of the example. And again, I invite you to follow along and read all this text. I cannot read it because it could be like a 3-hour sessions. But just go to a Colab and read all the details, go to the links, and understand everything that I'm, for obvious reason, not saying this was written by people way more intelligent than I. It's worth it. So here we're doing the post-training quantization. And in this, for this process, what we do is we need to wrap our data set in this NNCF dataset object that will allow the conversion to actually happen. It takes some statistical measurements about the data that we're going to be used that OpenVINO needs to make the actual conversion for the optimization progress. This takes a while. So whenever you do it, if you run this later in a different hardware, just be a little bit patient. It takes a while to run, but it's a necessary step for the model to actually be converted. And so now we already converted our model, and we can see that it's been saved to, we have different folders here. And each of these folders is actually a different version of the model. We have the segmentation converted to OpenVINO and converted to OpenVINO and quantized. So we now have 2 versions of each of our 2 models ready for inference. And so the next thing that we're going to do is we're going to validate that the model actually does what we expect. How are we going to do that? Well, we're going to feed it with known data, like this one. Do you see any difference? I don't. This is the output from the optimized model. So as of now, we don't see any noticeable difference, but that doesn't mean that there is not a difference, right? So we're going to run, the first thing that we're going to do, we're going to run a benchmark. We're actually run several benchmarks. First benchmark, we're going to run it on CPU. Using the detection model. This is the original model converted to OpenVINO framework. Then we're going to run it. We're going to feed a bunch of data to it, and we're going to take some measurements out of it. We can see that the first inference takes 29 milliseconds. That's very fast. Why can we run a first inference very fast? Because it's actually using the computer RAM, running from. Doesn't need to move a bunch of data to start performing. It just goes. After that, we're going to be running the same model on the GPU. So here, if we run OpenVINO model on CPU, we're getting 85 frames per second. This is already good performance, right? This is something usable depending on what our application is, the resolution of our image, etc. But it's actually pretty decent. Considering that the first version of YOLO that I tried had something like 3 FPS, right? And it was already considered real-time, an object detection model real-time. If we run it on GPU, first thing to notice is that the first inference is way slower. Why is that? GPUs work in a different way. They need to access the data in a different way. So the first thing that we need to do is we need to actually put the weights of our model in the actual memory locations that they need to be for this run. But once it does, look at the throughput. We are at 1400 FPS. So way faster running on GPU. Without doing anything else, just converting to OpenVINO and making it use the available GPU, which cannot be used from PyTorch. It can with an extension, but it doesn't come any close to this particular performance. If you want to know how, we can talk about it later, and I can teach you what you need to set up to actually make that comparison, if that's something that you. Next, the segmentation model. No, wait. The same model, quantized on CPU. So we're comparing our detection model on CPU versus our detection model quantized on CPU. Almost 3 times faster, right? We have 210 FPS when running on CPU. What happened here? The nature of the data changed, right? The nature, how we are encoding the weights, went from floating point 32 bits to an integer 8. So it's a much smaller data type, and its representation is continuous. It's constrained to the part of the information that's actually relevant to be useful for our data set. And then what happens if we take this same model, quantized, and run it on a GPU? Well, it actually runs a little bit slower than the floating point. Why is that? Because GPUs work better. Okay? So, something to take away. Yes? Yeah, maybe. It might have less, fewer kernels and fewer operators for that. Honestly, I don't know the actual reason. I just know that usually, if you're using a GPU, I personally convert my models to FP16. For inference. And you usually train in FP32 for inference. Like modern GPUs, FP16 tends to not get a hit in vision and still perform faster. If we look at the instance segmentation model, out of the box on GPU, we have a performance of 900 FPS. Pretty impressive, given the nature of the task. And if we take the int8 model, very similar performance. Why is that again? On GPU, we won't see the same kind of gains that we will see on CPU with these changes on data type. So that's why it's important to know what our deployment environment is going to be, what's the hardware that I have available, and make the best decision about that, what version of my model of quantization we're going to. Yes? Yeah, so that's a very good question. So usually, and I say usually because there are a few exceptions, machine learning models work with a fixed sized input. In this case, our input is, I think, 640 pixels. There's a conversion here. Just give me 1 second. Yeah, it's 3-channel. What do you mean, how deep? Mm-hmm. Yes. Mm-hmm. Yeah. So that's actually what happens when you quantize. Your model might generalize better to data that is away from your distribution before quantization than after quantization. But because you're quantizing and calibrating against a certain data set, if you feed it data that's close to that distribution of that data set, you're going to be fine. If you take an example that's away from the statistics of your data set, it will perform worse. So you lose that part. Usually, your machine learning model will be deployed to perform a constrained task with a constrained nature of data, right? So this is what we are thinking about. If the machine learning model that you're deploying is going to see like many different distributions, and you need it to generalize for everything, one, it's going to be a very large model first, and then you might not be able to quantize it or get the benefits of quantization, as you might if you are steering it towards a very constrained set of tasks. Yes, but I would say that it works well on most machine learning tasks that are going to be deployed to perform a particular task, right? Machine learning tasks that are going to be deployed as part of a service to solve one specific part of information. For example, if you're doing face recognition, your object detection only needs to find faces. It doesn't need to find anything else. So it will be specialized for that. Yes. So I have a lot of experience in computer vision. I have some experience with language models. This particular example is built around YOLO V8, which is a computer vision example. The same technique can be applied with different algorithms, obviously, to language models. And if you are interested in learning about that, you can come to this repository on the examples, notebooks, and the ones that start with 2 are usually examples of state-of-the-art models. There are a couple very, very interesting. Yeah. And then if you compare like the implementation of the different examples, you will see that the authors actually chose different algorithms for different kinds of models. And so there's not like a single path to everything. So if we come back here and we want to look at what was the hit? What did we lose? Well, we went from 521 to 515, and from 0.370 to 0.357. So we did lose some precision, but it's very small hit, enough that usually, if we are talking about second decimal or third decimal, it won't be relevant usually for a particular task. Again, this depends on what is your model being used? What are your requirements? What is your business case? Yeah, so here we went from FP32 to int8. So it's a data. You sacrifice something, yeah. And then if you use like traditional techniques for quantization, this hit used to be like 30%. Like it was hard. Yeah, so it depends on the kind of you go to here and go to, I'm just gonna search for Intel NNCF. Is the actual framework. Here. You're gonna see that there are a lot of different kinds of quantization that you can do. From those quantizations, you can use different algorithms for each kind of quantization, and you'll see like when you should be using one, when you should another one. Yeah, so you can do pruning of the model, you can do mixed precision, you can do full integer. Yeah. Yes. Medical images? I have no experience with medical data. Most of my data is commercial data, security, and finance. I know it's used. I know Google claimed a few years ago that machine learning models were expected to be better than doctors 5 years from now, and that hasn't happened. So I don't know. Do I think it's useful? Yes, of course. Do I use it? Yes. Is it a replacement for experts? No. Should I trust cancer diagnosis against a bunch of human doctors? Maybe not. I don't know. Okay, so that could be the example. So if we remember what we did, we loaded a pre-trained model using PyTorch. We verified that it worked. Then we converted it to OpenVINO. Automatically got some gains in performance. Verified that it worked. And then we quantized it, watched it perform way faster, particularly on CPU, and verified that it changed a little bit, but not enough to be a significant impact in performance on a real use. So yes. Not from a quantized model. I think you can convert from OpenVINO to PyTorch, although, yeah, I'm not sure how that might work. I've never tried it. Might be possible. So currently there is no training in OpenVINO. It's a framework designed to optimize on inference time. And yeah. And in my experience, once your operation starts really using machine learning in production, these are two different teams. One team is taking the pre-trained models and deploying them, and a different team is working with the data, making it better, making it not worse than the last version. Yes. That's correct. And those would be usually what in embedded systems they call it NPU, neural processing units. So if you look at like small processors, that's how the industry is calling them. If you go to like higher level computing, they call it like neural network accelerators or neural accelerators. If you go to servers, I can't remember how Amazon called their silicon. Google call it TPU. So that's basically that. And what it is a very, very small, a very simplified version of an ALU, specialized to be very, very fast, consuming very little energy for this limited set of operations. Yes. Yeah, so all of these have like integrated into the same die. So that would be me. Any other question? No? Well, thank you very much. I hope this was interesting. Did you learn something today? Awesome. Thank you.